Look at the stars in the night sky. Your imagination widens and you can think how big our universe is. Here is the Hubble Deep Field image. The Hubble Deep Field image provides the glimpses of most distant galaxies of the universe. These galaxies are seen as they were just 500 million after the Big Bang. Recently, the James Webb Space Telescope amazes us with its spectacular images of the very deep universe. From the James Webb Space Telescope, recently the image of the oldest galaxy is also revealed. This galaxy might have formed just 300 million years after the Big Bang. It revealed the oldest star cluster also. But the beginning of the universe is much deeper in time scales. In fact, the universe is too big. As of now, the universe is approximately 93 billion light years across. You just see a tiny window of the universe in your night sky. Now you can have a question: how these stars might have originated? What is the beginning of our universe? The modern day cosmology answers these questions. The cosmology realizes that the universe have originated from the Big Bang singularity. From before understanding the hot Big Bang, the universe expanded up to the evolution of and our universe. It will expand further. The evolution of the universe is explained by Friedman equations. These two equations has its own greatness. These equations govern the evolution and expansion of the isotropic and homogeneous universe. In these equations, A is the scale factor, rho is the density parameter, P is the pressure, these variables are all in the functions of time. Here, the G is the Newton's gravitational constant, lambda is cosmological constant, and C is velocity of light. In the Friedman equations, there exists a parameter which is called as K. The parameter has three different values. Either the above Friedman equations minus solution which corresponds to Einstein's flat and open universes respectively. Here is Einstein field equation is explained as an image. Here every parameter has its own meaning. The equation has metric tensor, stress energy tensor, Ricci curvature tensor and scalar curvature. In addition to that, there is a parameter called the cosmological constant. As we discussed earlier, the cosmological evolution in the beginning of the universe starts from the Big Bang singularity. In fact, at the Big Bang singularity, Einstein's equations break down. The curvature and density parameters at the Big Bang singularity approaches to infinity. To understand the Big Bang singularity, new set of approaches are required in order to understand the nature of the Big Bang singularity. The orthodox quantum mechanics and theory of relativity cannot be applied directly within this singular point. So, the nature of gravity has to be refined with a new quantization approach. Hence, the quantization of space-time is attempted with such approach.
The classical cosmological model does not provide detailed information about the dynamics of the universe at the singularity due to the vanishing scale factor. The initial singularity is the mysterious problem for any theoretical predictions. The classical attempts could not resolve the initial singularity. Hence, a quantum treatment is required to analyze it. Here, the loop quantum gravity emerges. With the help of background independent resolution, the loop quantum gravity provides a tool to understand the quantum nature of the Big Bang. The classical singularity is a mathematical point in which the cosmological parameters such as energy conditions, pressure, and curvature face divergences. The canonical quantum gravitational formalism, based on the quantization of the metric, it attempts to quantize the phase space as Hilbert space. In canonical formalism, the phase space variables are replaced by operators. The model has numerous successes in resolving the initial singularity. The model provides background-free solutions for the canonical gravity approaches. The loop quantum gravity explains the discrete nature of the space-time.
The so-called quantum gravity approach has its most success in the view of loop quantum gravity. The resolution of Big Bang singularity with the help of loop quantum gravity makes sense of understanding the evolution of initial stages of the universe and even extend its evolution beyond that singular point.
In order to understand the quantum gravitational nature of the singular, the Azteca variables are proposed. The first two equations in this page are Azteca variables. These variables are the connection variables and its conjugate momenta variables. Here, the parameters such as P and C are defined in 3 and 4th of the equation, and they are satisfying the commutational relation as the following way. In fact, these terms provide the new set of variables that can be used to understand the quantum nature of evolution of the universe as well as the quantum nature of the singularity. So the classical variables which cannot be implemented on these regimes, these Azteca variables will come to recover the evolution of the universe in order to understand its deepest meaning. The triads can be written as a densitized form. The densitized triads can conjugate the extrinsic curvature coefficient, which is written as KIA. Triad variables satisfies the following relation. Hence, the curvature is replaced with Azteca connections.
For the loop quantum gravity and its quantization approach, the phase space is being replaced by Hilbert space. Hence, the phase space variables are replaced with quantum gravitational operators. To understand the quantum evolution in the Big Bang singularity, the application of loop quantum gravitational formalism is implemented on the cosmological singularity as the loop quantum cosmology. Using the formulations of the loop quantum gravity, the loop quantum cosmological phenomenon is being derived.
On cosmological scales, loop quantum cosmology is proposed for the unperturbed evolution of the universe. The loop quantum cosmology is based on the canonical quantum gravitational formalism. The loop quantum gravity does not require renormalization. That makes the loop quantum gravity stand special over other quantization approaches. From canonical quantization, one can expect non-zero discrete values for geometric quantities such as quantum observables. Hence, the loop quantum gravitational approach provides non-zero values for area and volume. The area and volume in loop quantum gravity are formulated as operators. The classical phase space variables are promoted as operators in canonical formalism of loop quantum gravity. These are all explained as the following operators. To resolve the singularity conditions, the loop quantum cosmology is equipped with application of discrete loop quantum gravitational approach. In fact, loop quantum gravity attempts to derive non-perturbative and background-independent quantization of general relativity. The loop quantum gravity is based on symmetrical reduction. The new quantum variables beta and v can be introduced in the quantum regime in order to construct the quantum theory of gravity. The conjugate variables beta and v satisfies the commutation relation as the following way. Where V is equivalent to A3 and gamma is equivalent to 0.2375, which is the Barbaro-Immirisi parameter. The phase space variable from the classical dynamics are obtained as the equation beta is equivalent to gamma A dot by A. The parameter lambda determines the minimum eigenvalue parameter of loop quantum gravity and the discreteness of quantum geometry. The lambda parameter is defined as the following way. In fact, the effective Hamiltonian is written with the help of modified variables such as beta and v. So, the loop quantum cosmology sees the evolution with the help of modified parameters. And finally, the Friedmann equations can be modified using the variables of loop quantum gravity. In contrast to the critical density, which is obtained in the standard cosmological model, the critical density in loop quantum gravity is obtained as the following value. In fact, the critical density, which is very near to the Planck density. Similarly, expansion of the universe is governed by the second Friedmann equations, which is written as Raychaudhuri equation, with the help of the effective Hamiltonian and beta parameter, that is written as the following way. The great success of loop quantum gravity as it discovers that the space-time behaves with discreteness near the Planckian scale. Now let us understand the second quantization of loop quantum gravity. In fact, it is defined as covariant formulation of loop quantum gravity. In fact, the entire formalism of retrieving the classical relativity from the loop quantum gravity formalism lies on this following pathway. It starts with emergence of space-time phenomena. You can understand how the space-time emerges. In fact, this aspect is being treated by various formalism, especially loop quantum gravity, and the second quantization of loop quantum gravity is being extended to some other formalism named as group field theory. We can discuss group field theory in detail later. Then, from the emergence of spacetime, the emergence of quantum states can be observed. The quantum states is being extracted from the background emergent spacetime. Then from those quantum states, the tensor networks are extracted out. Using the tensor networks, the traced metric of quantum spacetime is retrieved using the formalism or the mapping on background independent quantum spacetime formalism. Then the classical relativity in its huge scales is being retrieved. So the mapping from the emergent spacetime to classical relativity is the idea to be understood in greater details. Second quantization of loop quantum gravity lies on the spin network formalism. Earlier, we have discussed the canonical formalism of loop quantum gravity that includes the Astaker variables, which converts the standard phase space variables into new set of variables. Similar to that, the second quantization based on the Feynman diagram formalism. Using this approach, the second quantization is implemented on quantum gravitational formalism. In fact, the configuration variable is SU2 connection in a 3-manifold. The corresponding canonical momenta is given by triads as we seen earlier. The local SU2 gauge freedom makes rotations of triads and transforms connections in addition to usual diffeomorphisms. The constants are represented in terms of connections. These connections are given below. Here, Gi is the cost constraint. F BA, K is the curvature of AIA, and DA is covariant derivative, and CA is vector constraint which generates deformism, and S is scalar constraint. In the auxiliary Hilbert space, the parameter required in the above relations behave as operators. In fact, the given constraints are being converted into operators. They give such a relation. These constraints form the Hilbert space. Such a space is called as physical Hilbert space. The quantum dynamics of the covariant loop quantum formalism, in fact the second quantization of loop quantum gravity, is encoded by constraint equations. The covariant loop quantum gravity has the holonomies along the path. That give the understanding on the fundamental excitations. The spin form formalism applies path integral formalism to understand the evolution of the quantum geometry, as we suggested earlier. The geometry is constructed by a series of quantum states of spin network states. These histories contain multiple transition amplitudes between spin network states. For any two instances, one can obtain transition amplitudes. These transition amplitudes determines the evolution. Hence, transition between spin network states are written as transition amplitudes. As a whole, the evolution is explained as the spin form formalism for the quantum cosmological phenomenon.
Using these formalisms, one can understand the evolution as the growing and the cyclic kind of evolution over the classical Big Bang model. But beyond this aspect, we can ask a question: how the singular space-time can emerge in a loop quantum gravitational evolution? To answer these questions, the new model called groove field theory emerges. This theory extends the loop quantum gravity formalism into greater depths. The theory attempts to answer how the space-time emerges before the big bounce using the spin network evolution. The model enquires the singularity using the spin form formalism and solve it for vacuum states. Here, the vacuum state refers the emptiness of universe and even the emptiness of space-time itself. Groove field theory vacuum is mimicked as the pre-geometric scenario where the quantum geometry of space tends to have nullification. The groove field theory has the infinite possible universe states, and it deals the model of the universe as resemblance of Bose-Einstein condensate. Instead of
the Hilbert space in the spin network formalism, the group field theory works as the Fock space where the corresponding Hilbert space is part of it. The theory suggests that from the vacuum, the group fields are created and annihilated. The creation and annihilation operators determine the evolution of the spacetime. The creation operator creates the atom of space, which is a spin network graph with edges, faces, and vertices.
As a conclusion, we can understand that the group field theory has evolved itself beyond the loop quantum gravity. The loop quantum gravity has done a great revolution by resolving the Big Bang singularity, but group field theory has moved beyond that. With larger degrees of freedom, the loop quantum gravity equations can be revisited in group field theory. As a result, new set of theories can emerge. The other fundamental theories, such as string theory, can also adopt the group field theory. These approaches will help us to understand the nature of the universe in very deeper levels.